Okay, good morning. Let's start the seminar of today. Today's seminar will be given by Dr. Yuhei Iwata on high-velocity molecular clouds near the Galactic Center, and Rainer will introduce him. But before that, we can show this marvelous video that was released yesterday. There was the touchdown of a spaceship on a surface asteroid, and you can see the small fragments that the impact liberate on this very low gravity object. And then this sample will be put in a capsule and sent back to the Earth arriving in 2020. So we can analyze the samples from the surface of the asteroid here in the laboratories. In other news is that the seminar for next week will be on Wednesday, because this place is busy, is occupied for another activity. So next week will be on Wednesday. And okay, Rainer, if you want to introduce the speaker, and I will leave because I have a meeting in the next room, very important one.
Okay. Thank you very much, René. So good morning, everyone. Our speaker is Yuhei Iwata from Keio University in Yokohama. He's visiting us this week together with Shogo Nishiyama, who is for those of you who have been longer here, he's a very well-known guest also here at Granada. Shogo has been here many times. He likes it a lot here, and we work together on the Galactic Center. He's the famous Nishiyama extinction lawyer, Shogo. And Yuhei is doing his PhD thesis in radio astronomy, so his research interest is radio astronomical observations of the Galactic Center. And yes, he will talk about the most exciting aspects of their recent research. And yeah, he's also, from his university, the Galactic Center workshop this year will be at his university. I think that Yuhei will say something about this. So please, it's up to you now.
Thank you, Rainer. Hello, I'm Yuhei Iwata from Keio University, Japan. Today, I will introduce the title of High-Velocity Molecular Clouds near the Galactic Center. These are the collaborators, and the background picture is which I took is the Nobeyama 45-meter telescope in Japan. We often use this telescope. First of all, I would like to introduce myself. I was born in 1993 and grew up in Yokohama City. Yokohama City is here, and the capital of Tokyo is located here, so very close to Tokyo. Yokohama is Japan's second largest city with a population of over 3 million. From 2012, I'm in Keio University. And now I am a PhD student in Keio University. Oh, this is the photo of in Yokohama. My hobby is coffee, both of drinking and brewing. And I also like the taking photos. HVCCs are in the highly excited, and it means that the local energy injection is occurred. We suppose that the possible origin of such events are the local explosive events and association with compact massive objects. Then I will show you some examples of HVCCs. Firstly, I'd like to introduce the L=1.3 region, this one. This region is known as L=1 plus 1.3 degree complex. The left panel shows the velocity integrated map, composite map of HCN and HCO plus and CO molecular lines. And the right panel shows the position velocity map of along this line. You can see some ellipses in the left panel and right panel. This feature means the expanding motion. In this region, it is reported that there are 9 expanding shells. The SIO emission is observed. The contour is SIO emission, and it means the association with the SIO emission means that the shock wave passed this cloud in past, because the SIO is well-known shock tracer. To explain this fact, supernova explosion is plausible. To produce a lot of supernova explosions, the stellar concentration, in other words, massive stellar cluster is needed. Considering the total kinetic power of the shells, it should be associated with 10 to the 5th to 6th solar massive stellar cluster is needed. This is the about 1 order magnitude greater than the masses of arches and quintuplet, which are the arches and quintuplets are the massive cluster in the galactic center. In spite of this heavy mass, no infrared counterparts are found. The lack of counterparts in other wavelengths makes the interpretation difficult. And secondly, I will introduce the L=-1.2 degree region. This is located at the symmetrical position with the L=1.3 region. In the L=-1.2 region, 5 expanding shells have been found, as the case of the L=1.3 region. The top figure shows the velocity integrated map of COJ=322 emission, and the bottom figure shows the longitude velocity map of this cloud. I think it is difficult to recognize the shells the circles of them. But we can see the expanding motion if we see the velocity channel maps, which means the slice of the data. We can estimate the expansion time of each shell, measuring the expanding velocities and the sizes. This figure shows the calculated expanding time versus galactic longitude of shells. You can see that the expansion time of the shells increases as the galactic longitude decreases. So this gradient. This situation means that if there is associated with a massive stellar cluster, the cluster is moving from galactic west to galactic east with respect to the interacting molecular gas. This figure shows the schematic view to explain the formation scenario of L=-1.2 region. This is proposed face-on view of the CMZ. There is known that the two arms, arm 1 and arm 2, is in it. And this direction is to the sun. Sometimes the clouds in an arm falls to the other arm, such as these falling, and also this falling motion. So if a cluster in the arm 1, cluster is in arm 1, and molecular gas in arm 2 falling and interact the cluster, it will explain this gradient and explain the formation scenario of L=-1.2 region. However, the big problem is that there is also now the IR counterparts near this region. And next, I will introduce an HVCC at longitude of -0.4. This is known as CO -0.40 -0.22. This is in here, and this is the CO -0.40 -0.22. The left figure shows the observed data of this cloud in the emission of SIO. This is the velocity integrated map, and this is the position velocity map along this arrow. You can see a slight velocity gradient in the position velocity map, like this. We tried to explain the kinematics of this HVCC, and finally we could reproduce the behavior of the position velocity map by using particle simulation. This figure shows the result of the simulation, and the top panel shows the about 5 seconds away from Sunshine star. This exhibits high COJ equals 3 over 0 intensity ratio. And the mass is estimated to be about 10 to the 5th solar masses, and it has energy of about 10 to the 51st erg. Because of this high energy, this cloud supposed to be formed by a series of supernova explosions. This is the position velocity, longitude velocity map of this cloud along this line. You can see this cloud had very high velocity width, and it has the system velocity is about 50 km per second away from near the cloud. Then I will explain the preceding studies of this cloud. The left figure shows the velocity integrated map in the CO J equals 4-3 line. You can see the arc-shaped edge and the emission cavity corresponding to the arc. And this figure shows the mid-infrared image, the same region of this. And you can see the group of point-like infrared emission in the emission cavity, like this. It turns out that, in this situation, this cloud CO 0.02 minus 0.02 may be associated with young massive stellar clusters, and the candidate of the clusters init, and the stars, the supernova explosions of the massive stars init, then it creates the high energy of this cloud. And then I am now studying this cloud, and this figure shows the velocity channel map of the CO 0.02 minus 0.02. The position and longitude and position is listed in here. This is the 80 km per second and 90, 100, and 110. And I confirmed at least 3 expanding shells are in it. The S1 and S2 and S3. The latitude velocity map of these shells are these 3 panels. This is for the S1, so here, and this is the S2, so here. This is the S3. You can see such as ellipse feature, and this is the expanding motion. This feature was found in this is the CO J-code 4-3 line, and this is also confirmed in the HCN J-code 4-3 line. This is the high density probe. So it means that these features are very dense and excited. So it may be associated with some explosion events, such as supernova explosion. The velocity range of this feature found in the range of 80 to 120. And I also performed a line survey toward this cloud. Line survey observations is to obtain such a wideband spectrum of the cloud. We can see the many species of molecular line like this. I performed in this observation using Nobeyama 45 meter telescope and got the range of 81 to 116 gigahertz. The line survey observations can examine the chemical composition of cloud. In this observation, I detected 64 lines, and this is the 32 species. And we can find some shock tracers, such as SiO and methanol and SO lines. And I tried to search the intensity ratio. The intensity ratio of SiO over H13CO plus is useful as the shock probe. This is the spectrum of SiO line, and this is that of H30 CO plus line. The horizontal axis shows the velocity and vertical axis shows the intensity. And this figure shows the ratio of these lines. You can see this ratio enhanced in the velocity range of the blue shaded area. This is the 17 to 110 km per second. And this is because this is the shock tracer, so this supports the supernova-driven scenario. This velocity range is corresponding to the velocity range that we observed these shells. And from this, the proposed stellar cluster, which was observed in the mid-infrared Spitzer image, should have a systemic velocity of about 19 km per second, which is this area, this velocity range. And now I am trying to study about the from molecular line and also the infrared. And then finally, I will introduce the recent results of the HVCC. I will introduce the HVCC HCN minus 0.009 minus 0.044. This figure shows the velocity integrated map of HCN emission in the galactic center. This is the circumnuclear disk, and here is the Sagittarius A star position. And this is CO minus CO 0.02 minus 0.02. And here is the position of HCN minus 0.009 minus 0.44. There is two giant molecular clouds near the circumnuclear disk, which are the minus 0.02 minus 0.07. This is also known as 50 km per second clouds. And there is also the GMC, which is known as 20 km per second cloud. This HVCC seems to stem from the 50 km per second cloud, like this. This is the velocity latitude map along this line. And this cloud is about 7 parsec from Sagittarius A star and more compact than any previously known HVCCs. Recently, we performed ALMA observations toward this cloud. And this figure shows the intensity map of the cloud in HCN Jacob 4-3 line. And this figure shows the velocity field of this cloud. The blue means the blue shifted gas, and left means the left shifted gas. Performing ALMA observations, it resolves HCN minus this HVCC to be the balloon structure and stream and ultra compact ultra compact sources in, like here. And inspecting the velocity field of this cloud, you can see this gradient in balloon and stream. This is the smooth data of this panel. And you can see the clear rotational motion of this cloud in both of balloon and stream. We tried to reproduce this feature, this velocity field, by calculating, by performing the simulation, particle simulations of the two clouds and one compact massive object. And we performed the simulation. The setup is the massive objects in here, at the position of star, and the simulated velocity field is this one. We located massive objects which have a masses of 3.2 times 10 to the 4th solar masses in it. And then we can reproduce the velocity field. You can see the same very likely structure. Only suppose one mass is in it. And interestingly, we can observe the Paschen alpha emission in the inside of the balloon. The contour shows the Paschen alpha emission, and this is located in the balloon. This situation is nearly to that of Sagittarius A star. So, and we cannot find another counterparts in other wavelengths. So we conclude that this cloud harbors an inactive black hole. And the mass is very high, so this is a candidate of intermediate mass black hole. I think many of you think that why the black holes cannot be found in the X-ray. But the number of black holes in the CMZ, in the Milky Way galaxy, is in terms of observations in X-ray, there are less than 100 black holes were found. However, the theoretical estimation indicates that there are 10 to the 8th to 9th black holes in the Milky Way galaxy. The black holes which we can observe in X-ray is which have binary, black hole binary, so which have the high accretion rate. So we think most black holes are inactive. So we cannot find in X-ray or some other wavelengths. And thus, we think that the searching for these objects from the molecular line, molecular gas, is useful to find these objects. And this is a summary slide. Dense stellar clusters and intermediate mass black holes should be lurking in the galactic center region. And high velocity molecular compact clouds could be the new perspective to search for these projects. And if you have any interest in this study, please come to the conference in October, and let's talk in this October in the Keio University, Japan, Yokohama. That's all. Thank you for listening.
Let's time for some questions.
Thank you for your talk. You mentioned several times high line ratio between different CO transitions in some of these clouds. But how high is it? Like a factor of 10? Or how high was the ratio between the 3 to 2 to 1, 0? The ratio. The line ratio. Is it a factor of 10? 5 or how much?
Oh, yeah. This is the CO emission creeping with the greater than 1.5. The ratio greater than 1.5. Yeah. Yes. The two lines? Yeah. Have they been observed with the same radio telescope, with Noviyama? No. We cannot observe in the observed of COJ equals 3229 in Noviyama because the telescope has limited the frequency. So my question is,
how do the beam size compare when you observe the three? Because if the 3 to 2 observations were observed with a smaller beam, then you would naturally have a higher intensity in your observation. Have you? Yeah.
The smoothing smoothing procedure. So yes, same same pixels. Yeah.
Thank you. Your finding of this intermediate black hole, that was very interesting. Is that the only object that has ever been found in this region, or are there more examples of intermediate black holes that have been?
Black hole in the CMZ.
If there are more examples.
There is no definitive examples in the CMZ, but there is IRS 13, which is very close to the Sagittarius A star. It's a candidate of intermediate mass black hole. And I also mentioned that this cloud may harbor intermediate mass black hole. But yeah, that intermediate mass black hole is very rare.
So I have a question. How do you define these shells? You say you find shells, and is it done by, I mean, I know the galactic center region in the infrared, and there's many things that are suggestive to the eye. But they turn out because you have a large region with a lot of random effects. So how do you define these supposed shells from supernova explosions? This, for example.
Yeah.
Because it looks like a shell, or do you have a strict criterion?
We have no criterion, and we confirm this feature by eye, but it's difficult to confirm it's difficult to set such a model fit, is because the molecular gas is often not exist like like this. So we need to see the data in detail. I think it's difficult to explain how to such. So sorry.
No, I understand. And to have SIO emission, how strong a shock do you need? I mean, there's strong turbulence also in the galactic center. So can it be induced by turbulent shocks without supernova? Or by forming young stars, young stellar objects?
A candidate of the SIO emission, I think. But this cloud needs the expanding motion. So the expanding motion and very high turbulence, it needs some explosive event. I think it is supernova.
Yes.
So I agree to the idea that the most of the black holes are inactive in our galaxy, but in your case, your candidates are interacting with molecular clouds. So can you explain why you cannot find any counterpart in other wavelengths, such as X-ray or something?
In this case, we think that these gas are not informing, not accreting in the black hole. We assume that these gas are just orbiting around the black hole. And in that case, the accretion is not occurred, I think.
I have a provocative addition to this question. So we know Sagittarius A star does not accrete much. It accretes maybe, I don't know, 10 to the minus 7 solar masses per year and has an adding luminosity of 10 to the minus 9. So it's like the example of a non-accreting black hole. Nevertheless, it's an extremely bright radio source. So if you have a 10 to the 4 solar mass black hole, I can just be very naive and just say, okay, if it's non-accreting, some gas is there. There is interstellar medium always in the galactic center. It's dense. So I would expect it to be 100 times fainter than Sagittarius A star. That would still be a pretty bright radio source. That is, I think, a question you should try to address, because you don't have a radio point source either. So it's not, you don't have counterparts at other wavelengths, you do not have a counterpart at any wavelength. So that is a point, I think, that needs to be addressed.
Yeah, we think that it should be detected in radio band. Yeah, and in the case of the CO minus 0.40, in the case of this, the compact radio source was determined by ALMA observations, but it is the controversial. But yeah, we think that it should be detected.
I don't want to be discouraging. I mean, I think this is very, very important, but I'm an intermediate mass black hole skeptic, at least in the galactic center, because there have been many claims always, but never any convincing claims. So I really think this, but it's very, very tempting. I mean, it's highly interesting to follow that up. More questions? Okay, then let's thank the speaker again.